We're going to solve some equations using logs in this video. So the first equation that we'll solve is 2 to the 3x equals 2 to the 4x minus 1. So you find yourself using logs to solve equations when there are variables in the exponent. So in this particular case, since they have the same base to begin with, what I could have done is just set the exponents equal, which is actually one really effective way of solving equations when that's possible. But it's not always possible, so what I'm going to do is show you how I would solve this using logs. Since they both have 2 as a base, I'm going to take the log base 2 of both sides. So that's going to be my first step. So I have the log of 2 to the 3x in base 2 equals the log of 2 to the 4x minus 1 in base 2. Now what I'm going to do is I'm going to use one of the properties of logs, which is that exponents become coefficients. So I bring the 3x down, and then I bring the 4x minus 1 down. So the property that I use there is this one, that exponents can become coefficients. So that's a really important rule, and you definitely need to know it. So now what I'm going to do is, since they both have log of 2 base 2 in them, you can actually just cancel that out. But really what I've kind of done is I've used the property that the log of a in base a is equal to 1. So that's 2 of the properties of logs that I've used here, but really I just canceled it out. Anyway, now I have 3x equals 4x minus 1, and you can see that x is equal to 1 in that case. So that's one example. Let's take a look at another example. So we have 4 to the x minus 1 equals 32 to the 1/2 x. So in this case, they don't immediately have the same base. So anytime they don't immediately have the same base, actually in general, anytime I'm doing a problem that involves logs, I actually just use the natural log. So I'm going to take the natural log of both sides and get natural log of 4 to the x minus 1 equals natural log of 32 to the 1/2 x. And I will then use the exponents become coefficients property to bring down those exponents. And that's kind of the whole point of using logs, is to get the variable out of the exponent and kind of bring it down. The downside is that you end up with these weird logs all over the place, but whatever, they're just numbers. So now what I'm going to do is take a look at each of these. So the natural log of 4 is the same as the natural log of 2 squared, which by the exponents becoming coefficients property is 2 times the natural log of 2. And then by the same reasoning, the natural log of 32 is actually just 5 times the natural log of 2. So I'm going to go back and replace those. So I have this, and then I'm going to replace natural log of 32. Okay, so you can see there's a log of 2 in both of those, so you can actually just cancel that out. And then I'm left with 2x minus 2 equals 5/2 x, and you can solve that to get x equals negative 4. You might have noticed immediately that 4 and 32 are both powers of 2. So we could have rewritten the problem initially as this, which would have been a good idea. And that gives us this. And then what you're really doing here when you set the exponents equal is you're kind of taking the log base 2 of both sides and then canceling it out. And it's essentially the same as the first example that we did. But either way, you get 2x minus 2 equals 5/2, which again means that x is negative 4. So that's another option in this case. I probably would have done that, but if you don't notice that they're both powers of 2, you just dive in, take natural logs, and it's not a big deal. Let's do one more. So here we have 3 to the x minus 1 equals 4 to the x plus 1. I am confident that they are not both powers of the same number, or the same integer at least. And what I want to do is I'm going to take the natural log of both sides, and I'm going to use the exponent property right away. So I get the quantity x minus 1, natural log of 3 equals the quantity x plus 1, natural log of 4. Okay, so natural log of 3 and natural log of 4 are just numbers, so we can distribute them, we can add them to both sides, subtract them, whatever. So I'm going to distribute x natural log of 3 minus the natural log of 3 equals x natural log of 4 plus the natural log of 4. And now what I want to do is get everything with an x on one side and everything that doesn't have an x on the other side. So I will subtract x natural log of 4 from both sides and add natural log of 3 to both sides. So that gets me here. And then I can factor an x out of everything on the left-hand side there. So that's good. So I get this. And what I can do now is divide both sides by the natural log of 3 minus the natural log of 4. So I'll have this, which is kind of okay depending on what problem you're solving. But sometimes the problem will say write it as a single log, and this is not a single log. So what I'm going to do is I'm going to use two of the properties of logs that I know to rewrite this. So the first one, in the numerator I have the sum, so the natural log of 4 plus the natural log of 3. The way that I think of this rule is that addition outside of a log becomes multiplication inside of the log. So this will become the natural log of 4 times 3, which is obviously a natural log of 12. In the denominator, division outside of logs subtraction outside of logs becomes division inside of the log. So the natural log of 3 minus the natural log of 4 becomes the natural log of 3 over 4. And then I can rewrite this a little bit to get the natural log of 12 over the natural log of 3/4. What I could do now, so that's two more properties. There are a lot of properties of logs. What I could do now is I can actually use something called the change of base formula, because they both currently are logs that have a base of e, right? That's what natural log means. So I could rewrite it as x equals the log of 12 in base 3/4, which is really weird, and I probably wouldn't write it that way. There's actually a stranger way to write it based on what we've done so far, which I'll just write for you. You could have written the log of 1/12 in base 4/3. And where does that come from? Well, if you follow the work that I did in the box above that answer, and then go back to my original answer, kind of over here, if you imagine taking the negative sign that's in the denominator, factoring it out, distributing it to the numerator, that's how you end up with that answer, actually. But anyway, I hope you found these 3 examples kind of useful, and good luck.